Great, let's
Okay,
just check.
let's go for the next talk. Yeah, it
Oops.
works.
Hang on, too fast.
Okay, let's go for the next talk. The speaker is Bonnie Steve from Glasgow Caledonian University, and she will speak about analytical stability criteria for the Caledonian Symmetric 4 and 5 body problems.
Great. Thank you, everyone. I'm really pleased to be here at the 7th Chalmec. I think I have managed to come to 6 out of 7. And I was remembering the first time we actually presented the Caledonian problem, and I believe it was actually at something like the first or second Chalmec meeting many years ago. It's an analytical solution, and it's a little puzzle that Professor Archie Roy and myself worked on. And now since we've carried on the tradition, and it's work that is being done by myself and my former PhD student, now successfully in a lectureship in UAE, Shweb Afridi, and Winston Sweetman, who's in New Zealand now and originally started in Edinburgh. And what is the Caledonian Symmetric 4-body problem? Well, we started it as the 4-body problem, and recently we've done the full case of making it a 5-body problem. And so, basically, you have a line. They start in a collinear position, and you have the center of mass here, and you have symmetries on either side of the center of mass. And the key thing is that the bodies start collinear, and the velocity vectors are perpendicular to the line. And then you have used all sorts of symmetries in the problem. And you can have a symmetric mass ratio here, and the same on the other side. And additionally, put a central body, the 5th body, at the center of mass and fix it there. And with these special symmetrical situation, when you let it run, it will always be in a parallelogram in the plane, and you will have the symmetry of the orbit after this point will be opposite before it. So you end up with, if you go through what is known as a mirror configuration, this kind of line with the perpendicular velocities, if you go through 2 of those, you will end up in a periodic orbit. So it's a nice way to manage looking at a symmetric 4-body and 5-body with the center mass. So let's just have a look at what this looks like, and this is where I need to bring the cursor down. Whoop. And just just on the scene, up, and then there we go. So watch the bodies, and what you have is a change in the hierarchies. So you have different colors now. Diamonds and stars were on the symmetric side, and you can see them changing their order. And this allows us to explore the different kind of dynamic structures that you have and the different configurations in this symmetric problem. So sometimes you have double binaries, and sometimes they come into the center, and you have a single binary and the bodies on the outside moving. So let me just do that again. Okay, watch. The pairs, and this there's in the center. Now this is our first original movie when we were trying to look at how we could actually simplify a 4-body problem 17 years ago and actually get a handle on all the richness of the different configurations. So it's still a very useful demonstration. So what we thought, let's stop that. Okay. Is if we could actually map all of this and find a way to understand the different arrangements and the transfer from different configurations, that we'd be able to handle and get a kind of global sense of hierarchical stability. So hierarchical stability meaning it moves but it doesn't change its hierarchy, and a sense of how it changes between those hierarchies. So these are the 4 different hierarchies that are possible in the 4-body problem, and 5-body with the 5th mass put in the center of mass. And so you have those 2 arrangements of the double binary. So that's bodies 1 and 2, and then bodies 1 and 4, and they're symmetrical opposites on the other side. So we call that a 1-2 double binary, a 1-4 double binary. Those are 2 distinct arrangements. And then the other 2 was the single binary in the center going round the center of mass, central mass, and that is paired in 1-3 or 2-4, and then you've got the outer ones, 2-4 here and 1-3. So those are the 4 different hierarchical states that you saw. And we then thought, well, we actually might have a way, this is quite 4 bodies, quite a lot of dimensions here, but we might have a way with the symmetries, since we only need to look at one side of the center of mass. So you're effectively looking at the motions of 2 bodies plus the center of mass in terms of your dynamics, because what happens on one side will be symmetrically happening on the other side. And so we thought, let's look at the space, and we could define it purely with, whoops, sorry. Hang on. Purely with our distance to the first body, scaled, rho 1, our distance to the second body, scaled, so R2, and the separation between the 2 bodies, 1 and 2, on the side, one side of the center of mass. And the first thing you could do to find the area of motion is actually just have the kinematic constraints. So we were playing the game of basically carving out the space where these bodies could move. And the kinematic is, just as an example, so along this line here, you've got collisions occurring where your R1 is 0, and you have a collision set along this line. And so these are the kind of boundaries. You can't go beyond your collision in this problem. And then we went and cut the space out even further. So you're looking at the regions of allowed motion, so kind of 0 velocity curves equivalent. And this was specified at having angular momentum 0. And you could cut out the space further. So here we have, and you end up with 4 pipes. So we thought, oh my goodness, here's the bagpipes, and we're in Scotland, and we called this the Caledonian problem after my university, which is Glasgow Caledonian University, but also after Scotland, which is the Roman name Caledonian. So we had bagpipes appearing, and each of those configurations occurs in one of these pipes. So that's the regions of allowed motion. You can't move outside that. And we then thought we could cut it even further. So this is very much looking at including the angular momentum into the problem. And here, using Sidman's inequality, which is a feature of the physics dynamics, we have this relationship, and so it cuts the curve even further. So we have where we first developed that for the 4-body, and we've now extended it to the 5-body. just recently to have a complete set. And this is what it looks like when you write it in the equations with a few parameters. So you've got the R1, R2, the separation R1, 2, separation between the two bodies, and basically you've got the mass ratio of between the two bodies, and then the central mass coming in here. But there's a relationship there, so there's just two mass ratios that you're using as a parameter. And you have this constant, which we call the Zeebehe constant, which appears in lots of dynamical systems, gravitational dynamical systems. So you might have heard it in the three-body problem as a c squared h criteria and parameter. It's angular momentum and energy. And you see that in a lot of gravitational dynamical problems. You see that in the galactic problems, that this constant has some meaning in terms of looking at the sort of opening up of curves or changing of the topology of your system, and is used often in creating a stability criterion. So that's what we were quite interested to see that. And if I go back to the original picture, okay, what we found in the 3 dimensions, so this is 3 dimensions, when you had angular momentum included, you started to cut out holes into this where you had allowed motion. And we realized, because of the symmetries, that this pipe is sitting on top of this pipe, and that these pipes here are on the sides, and that we could actually project this down onto the 2 dimensions and get a sense of the maximum allowed areas of motion. And so if you just have a look at the shape of that projected down on the R1, R2, and R1 equals R2 line, you have this kind of shape. And so that's these 2 pipes projected down, and these 2 pipes projected here and here. And this allows us to actually look at the features. And if we go back then, I'm going to use these projections for a lot of looking at the characteristics. So you see, with the Sudman's inequality in that equation, Zeebehe's constant, C0, is actually the constant that deliberates the opening and closing of these spaces. So this is the area that you can move. So any orbit, any configuration, it's kind of moving around here. And in this one, it's a single binary, 1, 3. If you remember the hierarchy possible in here, projected down is actually the 2 double binary systems, and in here is the other single binary. If you increase your Zeebehe constant, your angular momentum and energy for the system to a critical point, which we can actually derive because these are all parts of equations, you can actually see that the regions pinch off and you have regions that you can't move around in. So this one you're able to change and change your hierarchical stability. Once you pass this critical point, it's cut off, disconnected. If you were here and as a single binary, you remain a single binary for all time, and you have hierarchical stability, which is really nice to see in a 4-body problem. So recently, we put the 5th mass into the problem and looked to see what you would get. So you have 4 equal masses in this case on the sides, and in the center we have a small central mass. So you think of that visually, 2 big masses on either side, stars, and a little tiny one in the center. It's not going to be very stable. in terms of being fixed there. But fixing it, having that type of Caledonian problem, this is the space that you see. So what we've done here is kept the masses equal on the outside. We've put in a very small central mass, 0.01 a hundredth, and looked at that plane. So for angular momentum energy of this size, you're free to change your hierarchies as much as you want. But actually, when you get to this critical point here, then you're pinching them off and you remain double binaries and single binaries. So there's a point where you can have hierarchical stability for all time. So for the problem. You note when you've got a small central mass that the dominant hierarchies are double binaries. So that's a relief because that's common sense if you've got two big bodies on either side. And down below here, we have a large central mass, and you see that the dominant is going to be the single binary in the center. So you've got a large mass in the center, at the center of mass, two bodies going around that in a single binary motion, and then the outer two bodies going around that configuration. So that all makes sense. So the analysis and the mathematics is showing what we know is common sense. And again, as you increase the Zeebaugh constant, or increase the angular momentum and energy, you have a point where you will have that single binary system maintained for all time. So you have hierarchical stability. For the non-equal masses, that means mass ratio on the side of the center of mass. And in this case, we've just taken a few examples. You have the same sort of disconnection occurring, but now it's done in two steps, depending on the mass ratios that you have in the two bodies on the side. So here's the case where it first disconnects with this single binary with the massive small central mass in the center, and then all of them disconnect, and you have hierarchical stability again for all time, for all arrangements. Whereas here, if you were in this arrangement, that single binary mode, you would be firstly in a hierarchical stability for all time. Large central mass, same sort of thing again. And what you have here, different from the equal masses, is simply just a change in the proportion or the area of real possible motion according to the mass ratios. So you can actually work out a relationship between having no central mass and having the central mass and looking at the size. So this is for the case where we have the two masses equal. So you've got equal masses on either side of the center of mass, and then you're varying the central mass. And so here's the four-body problem. And then you're increasing the mass, and you have the five equal masses, so a stellar case, and then down here a critical value of when you have a large central mass. And this, if you have the angular momentum energy of your system greater than this critical point that's given here, then you have stability, hierarchical stability of your arrangements for all time. So it's quite nice to look at a system, measure its energy and angular momentum, and be able to conclude whether it's hierarchical stable or it's actually going to interchange and change its hierarchies, which is what this shows you. And you actually can do that in two, include the other mass. So that was when the two masses were equal on either side. And in this situation, we've actually shown so that cut when the two masses are equal. And so we've got here the whole range of mass ratios And really the critical value depends only on the mass ratios. So you just need to look at what is the energy, angular momentum combination of your system to decide what were the mass ratios that you started with, and then you could actually work out whether it was hierarchical, stable for all time. It's a nice puzzle. So I'm going to finish with a few pictures so you can see what that looks like, and this is where I need to jump out of the video and hopefully this works. So this is the 5-body problem, and showing you the Caledonian Symmetric type orbit. It always is in a parallelogram, and you have that kind of single binary trinary in the center. And in that mapping, that projection, we were able to look at all the behavior. It was a nice way of looking at the behavior of all the different orbits, starting at different mass ratios and energy and angular momentum. And we could actually work out the regular areas, the chaotic areas, and identify periodic orbits in the symmetric problem. And so this isn't a periodic orbit, but it's close to one in that mapping. And finally, whoops, let's stop. Okay, hang on. Oh, I can hear. Oops, hang on. This one. So this is the double binary. Again, this isn't a periodic orbit, but it's close to 1. And it just continues like that. And then just recently, so we were looking at periodic orbits, and there's a fantastic poster on the Caledonian Symmetric problem of a new type of periodic orbit in the Caledonian problem. So here we have periodic orbits that have the double binaries, and periodic orbits that have the single binary and then going round. And then newly, Valerie, who is she here? No, she's got a poster in the foyer there that took the Schubert type orbits, which I will just skip to. And so that's part of her poster. She's a student of Winston, and they expanded it into the 2 dimensions and found these periodic orbits in the Caledonian Symmetric problem. So the problem lives on. There's lots of things to look at. And then just recently, I go back. Here is latest movie showing a planet that was discovered. Now this isn't exactly symmetric. It's not the Caledonian Symmetric problem. I'm still looking for the symmetric or close to symmetric problem, but we're getting closer. So this is actually an exoplanet system, triple star, but if you look at the emotions, they're starting to look very similar to our Caledonian Symmetric 4-body problem. Clearly the mass ratios aren't symmetric, and the distance is not quite. We did do some experiments where we broke the symmetry and followed the periodic orbits and some of the other orbits through, and where we had linear stability in the periodic orbits, when you broke the symmetry, that carried on. You could find other periodic orbits in the family with linear stability. So I will stop there.
Thank you. Time for a short question or comment.
Everybody's tired.
I think so.
Great.
Let's thank the speaker again.